This is the seventh and final video in the coupled oscillator series. In this video, we're mainly going to apply the general Lagrangian method for solving a coupled oscillator problem, and we will do so with this one, which is slightly more complicated than what we have attacked before, because we actually have three different coordinates. We have the three angles phi1, phi2, and phi3 that these pendulums make to the vertical. These pendulums otherwise have the same weight attached at the end, mass m. They're the same length, and they're all connected by two springs, each of which has spring constant k. So as usual, we'll start by writing down the potential and the kinetic energy. The kinetic energy is going to be the easiest. We know that the kinetic energy of each of these is going to be 1/2 m times now the velocity squared of each of these. Now we know that the velocity of the mass is just the angle phi1 dot times the length of the pendulum L squared. And same thing for the other pendulums. And we can rewrite that like this, but just pulling out the L squared in front. All right, that's the kinetic energy. The potential energy has two parts. There is a gravitational potential energy associated with the pendulums, and there's also an elastic potential energy associated with the springs. So let's start with the gravitational potential energy, and let's actually just to show how this can be simplified, I'm going to write down the gravitational potential energy of just the first pendulum. So you grab for the first pendulum, that's going to be, of course, mgh. Actually, it's called mgy. Y is the distance above the equilibrium point that the pendulum goes. So that's really just mgl 1 minus cosine phi1. Okay? Now, that's all well and good, but this is going to lead to a nonlinear system. So just like before, we're going to approximate the cosine with the first two terms of its Taylor expansion, which is valid for small angles phi1. So this is approximately equal to okay, and we can see that these ones cancel each other. So then you end up with mgl phi1 squared. So that's an approximation for the gravitational potential energy. So we can then write that in general, the full gravitational potential energy, FGR, is pretty close to being mgl phi1 squared plus phi2 squared plus phi3 squared. And if we were to stop here, then we'd just get three pendulums that are not coupled to each other, and they all oscillate by the same frequency, square root of G over L. So next we need to take into account the coupling of the pendulums to each other, and that is arranged through these springs. So we have to write down the potential energy associated with the springs. So we have an elastic potential energy, which is going to be 1/2 k, and then it's the length of the spring, which is then equal to the distance between this spring, between this mass and that mass, or rather at least its deviation from the equilibrium. We're going to assume that when all pendulums are vertical, then the springs are the natural length and the potential energy is 0. So then that just becomes, for the leftmost spring here, L phi1. That's the deviation of this mass from its position at the equilibrium. How far away is it from the point when it's right below its attachment point? Not phi1, phi2. And then it's L phi1 squared. And then same thing for the second spring. Okay, we can simplify that a little bit by, first of all, taking out all the L's. Every term here is actually proportional to L squared. And then we can actually take the squares here, so we get the explicit form 1/2 KL squared. So these are the two expressions for this is the gravitational energy, the elastic energy, and the kinetic energy. So I'm going to put these together on a single form over here. So we get that the total potential energy equals So you may note here that I actually wrote these terms 2, phi 1, phi 2 on the form phi 1, phi 2 and phi 2, phi 1. So minus 2, phi 1, phi 2 is minus phi 1, phi 2 minus phi 2, phi 1. That's obviously correct. And the reason I'm doing this is because if I have it on this form, then it becomes easy to to go directly from this form of the kinetic and the potential energy directly to the M and K matrices. Okay. So those are our kinetic and potential energies. Now, let's compare to the result that we found in the previous video. I'm going to make room for that, I'm just going to erase this. And that is that we can write the potential energy on that form and the kinetic energy on this form, where K and M here are the K and M matrices from before. Actually, let's just write this a slightly more explicit form. Let's not use this one. Let's just say that we have now we can see here that with the proper approximations, the kinetic and the potential energies are all quadratic forms of the generalized coordinates phi 1, phi 2, and phi 3. And using these forms now, we can directly read off what the members of the M matrix and the K matrices are. So for instance, we can see here, if we look at the potential and the kinetic energy, there's phi 1 dot times phi 1 dot. Whatever multiplies that, not including the 1/2 factor, is now the M11 term. So we know for a fact then that M11 equals ML squared. Same thing for M22 and M33. You can just read that straight off. And if we want to find the K matrices terms, well, we just look at the potential energy down here. And now it becomes clear why I wrote it on this form with phi 1, 2 and phi 2, phi 1. Phi 1, phi 2, and phi 2, phi 1, because these correspond, each of them, to the K12 and the K21 terms. And of course, the K matrix has to be symmetric, so you can't put everything in K. We cannot say that K12 is 2K and that K21 2, 1 is 0. They have to be equal, otherwise the K matrix would not be symmetric. So now we can just read it off here. We can say that, well, the 1, 1 term, K1, 1, comes from everything that multiplies 1/2 phi 1 squared, which is K plus G. So K1, 1 is K plus G. K2, 2 is 2K plus G, right? Because it says 2K plus G. Same thing for K, not same thing, but similar for K3, 3. But that's also equal to K plus G, just like K1, 1. And then we can read off the off-diagonal terms here. K1, 2 is equal to K2, 1, has to be equal to K2, 1, right? And that is minus K. And K2, 3 equals K3, 2 is also minus K. So now we have all the members of the K and M matrices. Note that we got that without writing down Lagrange's equation or even the Lagrangian itself. They just immediately come from the kinetic and potential energy, as long as we can write them on quadratic forms like this. So let's now solve this. To simplify things a little bit, I'm going to use what's known as natural units, which basically means setting certain things to 1. So I'm going to just say that L equals 1 and M equals 1. That's not necessarily the case, but it makes the calculation a little bit simpler, and then we can restore the correct form that includes M and L at the end. All right, so we have that the M matrix, using these natural units, is just a unity matrix. The K matrix is just this. There, right? And now to calculate the eigenfrequencies, we just have to calculate this determinant, as you should now be very familiar with. So that's just equal to okay, and that becomes so these terms so far come just from the diagonal, but it turns out that the terms of the determinant that involve the off-diagonal terms are also proportional to G plus K minus omega squared. So we then just get, and we know that this has to be equal to 0. Then we just have to now factorize what we have inside here. We can do that using the quadratic form, but one thing that you can see if you look carefully at this is that it's on the following form. You can rewrite that like this. Like that. So this is not something you have to memorize, but if you recognize this form in here, then you can see with B, of course, equal to K and A equal to G plus K minus omega squared. Then we will get that the determinant of K minus omega squared M is equal to G plus K minus omega squared times G plus 3K minus omega squared. times g minus omega squared. So that's our intermediate result. Right there. Okay. So now that I've done that, we can find out what the eigenfrequencies are. It's quite clear from this form, because this has to equal to 0. So that means that we have the eigenfrequencies, or the normal frequencies, actually. Okay. Now, of course, g plus k, they don't have the units of frequency, or frequency squared. But that's because we picked these natural units. So in order to turn these into frequencies, or squared frequencies on either side, we just multiply by the appropriate factors of L and M to recover fully dimensional forms. So in order for g to become a frequency square, we just divide by L, because we know that the square root of g over L is the frequency of a pendulum. Same thing for k. In order to turn that into a frequency squared, we take k divided by m, because we know that the square root of m is the frequency of a mass in a spring. So really what we get in the end is like that. Then to find the mode, as usual, we need to calculate the following. And I've chosen to start with the third mode. Of course, I could have started with any of them. Which then becomes and this equation I'm going to write over here gives us actually 3 different equations. The following ones. From the first equation, we find that A1 equals A2. And from the third equation, we find that A2 equals A1. So that gives us that A1 equals A2 equals A3. They're all the same. And then we can take this and plug it into this middle equation here and show that that's actually true. We have minus a plus 2a minus a is 0. That's correct. And this is a good sanity check to always make. Like I've said before, these 3 equations are not linearly independent. They are linearly dependent of one another. So if you take any 2 of them, that will give you this result, and then that should agree with the third equation that is left over. In this case, there was the second equation. And if it doesn't agree, then you've made a mistake, and you should check your math. So that's the solution to, this is what the mode looks like for normal mode number 3. move this out of the way there. And we can do the same thing for the other two modes, and if we do that, we will find and something that you should verify for yourselves. So I don't have a nice video for this, but I can just illustrate what this looks like using the original sketch from up here. So we have one mode, the third one here, where all the masses are moving in unison, left and right, all at the same time. The frequency of that mode is the same as that of a single pendulum, because the springs that connect the pendulums don't stretch or compress, so therefore they don't actually have an effect on the movement of an individual pendulum. Then we have this mode here, in which the central pendulum is sitting still, and the two outer pendulums are moving in opposite directions away from the center. And the second mode here, the outer two pendulums are moving in unison, whereas the central pendulum is moving in the opposite direction. Those are the three normal modes of this problem, which we found using the method outlined in the previous video, using Lagrange's equation, but without making explicit reference to it.